Everyone, this is my lab 6 for magnetic molasses, so let's get started. So the purpose of this lab is to analyze magnetic induction by recording a magnet falling through an aluminum tube and how this system's components interact with each other. I will compare real and computational models to drive our analysis today. But firstly, for our results, the experimental time was 1.28 seconds for the magnet falling through the tube, and the WebV Python time, or the computational model time, was 1.3 seconds, or 1.28, 1.3 seconds. So moving forward here, we mainly use the Biot-Savart law as well as Faraday's law to determine the time as well as calculations in this lab. But for our experimental setup, you can kind of see that we have an aluminum tube here as well as a magnet falling through it, and the system is the bar magnet, an aluminum tube, and the surroundings are everything else. But as you can see here, for our experiments results here, we have 5 different times that we recorded, and I guess the reason why there's some variance is that sometimes when we drop the magnet, there would be the magnet tumbling around, or perhaps we dropped it slightly differently at a different angle, and so that all constitutes to a variance in the actual trial times. But here are our measurements, our beginning measurements, which will be used in the computational model for the mass of the magnet, the mass, or in the length of the tube, and then here is our average out of all of these trial times for dropping the magnet into the tube. So moving forward here, this is my computational model. First we set the scene here, and we make the graph, and then next we kind of create the tube as well with the measurements that I mentioned earlier. And then we also create the magnet as well with the length or the radius that we mentioned earlier. And so then moving forward here, we use these different calculations and this main loop to then determine this result right here with this graph, as well as the time in tube being 1.31 seconds from the computational model. And then here we can kind of see that we model the tube as discrete circles that the magnet falls through. And so we can then see, as we move forward here, that as we compare the experimental time and the WebV Python time, some sources of error are that there's air resistance, the bar magnet acts as a magnetic dipole, which we kind of assumed, the tube is modeled as discrete rings, which you kind of see here, and the uniform material is aluminum tube, because there could be some specks of other materials in there as well. And then finally, the magnetic moment is constant. And so for our what does it mean questions, what if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? If the resistivity were reduced very close to 0, the magnet would fall much more slowly, and it could be almost suspended or descend extremely gradually. And if holes or slots were cut out into the tube, how would this affect the ring currents in your model? The magnet would fall faster because the holes would interrupt the induced current running through the tube, or in other words, the magnet would be closer to free fall. And so that is my lab 6. Thank you for listening.